Okay, we are going to be talking about the GD&T application on our Arbor press. Okay, so one of the focuses that we've had on this particular project is not only modeling and learning some new fun, challenging commands, but we've also been looking at tolerancing and fits. So we want to also incorporate GD&T where it seems to make sense on our designs. So if we look at this assignment, you're going to notice that I have 4 items listed here. So the first one is you're going to be applying GD&T position tolerances in 2 places. It's really not a whole lot of holes lining up with things in here. And it's really just that faceplate on the front of our Arbor press. So that's going to be one place that we're going to be applying it. And we're going to be talking about that specifically in just a little bit. And then I also want you to apply position on that very same faceplate for the number 32 or number 10, 32 threads that are on there as well. And we'll talk about how we can do that. All right. Now, additionally, I want you to find 3 places in this assembly. You get to pick to appropriately apply flatness. Okay. 3. Then you need to do another 3 for perpendicularity. Appropriately apply. So that means if it needs datums, if it needs basic dimensions, if, whatever it might be, you have to do that. Okay. And the same thing for parallelism. All right. Now, as we look at these, I'm not dictating where those are. So you have to then create a document for me identifying all the 11 places, including the 2. So I'm including the 2 positions that we're going to be going over today, that you're going to get 2 of them done for this assignment. Okay. But I want a document telling me where are the 11 places that you put the things, the flatness, the perpendicularity, the parallelism. Now, you can apply each one of these on a feature of size or a surface. I'm going to let you choose. Okay. Flatness doesn't have to just be on a flat surface, as we know. It can be on a center plane. Okay. So if you see an axis of symmetry and you want to apply a flatness on a center plane, you could do that. Same thing for perpendicularity and parallelism. It can be applied both to feature of size and a surface. Okay. So you get to pick how you want to apply it. But when you do, it has to be placed and appropriately datumed and such on the drawing. Does that make sense to everybody? Okay. So that's what this is. So it's really just letting me know where they are rather than me going through all the drawings and trying to say, okay, here's one of the flatnesses, another one of the flatnesses. This way I can focus a little bit better. So I just want a document of you letting me know where you applied 3 flatness, 3 perpendicularity, 3 parallelism, and the 2 positions. Okay. I know what the 2 positions are, but just include them in the whole list. Does that make sense to everybody? Okay. So let's look at those first 2, the positions, to go through the process of specifying those. So I'm going to go underneath my camera and we are going to be looking at it. And the first one we're going to see is the position of the 4 holes that we have on the front face of the top of our frame. Okay. And in this case, there are 4 1/4-20 UNC taps by 1/2 inch deep. Okay. And we want to position those so that they fit appropriately with our faceplate and the floor clearance holes that we have on the outside here. Okay. When we had gone over and we looked at the drawing guides, okay, you'll notice that there are zeros in the GD&T that I kind of placed in here. Okay. And that is because we need to come up with values. And that's what we're going to do right now. We're going to determine what is the value that we're going to put into that feature control frame to ensure that it will fit with the 4 threaded holes here on that front face. Okay, right there. So if you recall, I think some of you, not all of you, had me for GD&T, right? Some of you. Who had me for GD&T? Ooh, there's a lot. Okay. Okay, good. So that means you know everything you know. Maybe I don't even have to do this. You're like, got it. But it's been a little while. Okay. So we will go over it. So when we have applications like this, where we have threaded holes, we're going to be putting a fastener through here. And it's going to go through a first through a clearance hole, and then it's going to be threaded into another piece. There was two different types of conditions that we could have when we calculated position tolerance. One was a floating fastener condition, and the other one was fixed fastener condition. Okay, everybody remember that? Fondly remember, right? It's good stuff. So tell me, think about it for a moment. Is this a fixed or a floating fastener application? Okay, I'm going to give you about 10 seconds. Fixed or floating? Okay. For those who are virtual, I want you guys to put in fixed or floating in the chat box. For those in the room, raise your hand if you're a fixed, or raise your hand if you're a floating. Okay, so go ahead. Or I'm sorry, no, right? Just raise your hand if you're fixed. We'll do the first one. That's how it's going to work. Raise your hand if you're fixed. Oh my goodness. We've got floating, floating, floating. I have no hands up in the room. I know there's more than 3 people that are virtual. I've got like, I don't know, 6 or 8. Floating, floating. Oh man. More. Anybody in the room wants to put their hand up for fixed? Drew says he's thinking fixed. Joshua's floating. Okay. Josh in the back is a fixed. Okay. All right. Do I have everybody accounted for? I don't want any lurkers. 1, 2, 3, 4, 5, 6, 7. Okay, Jaden got in. He didn't want to be a lurker. Okay. Well, unfortunately, for those who said floating, you're wrong. It's a fixed fastener application. So a fixed fastener application is when we are going through a set of clearance holes and we're threading into something else. A floating fastener condition is when we are going through only clearance holes and we're fastening on the back end with a washer and a nut, if you would. Okay, that's the difference. Now, let's look at the equation for each one of these. Okay, I'm just going to go on the back of one of these sheets here. Okay. Now, this is something I'm sure you recall. So T is equal to H minus F. Okay. This is the equation for a floating fastener application. Okay. We aren't going to be using it today, but I think it's worth you just kind of remembering that's what it is. Now, T is the tolerance we're going to be putting in the feature control frame. Okay. So we're going to calculate that using the MMC size of the hole and the MMC size of the fastener. Okay. Now, fixed application is going to be T is equal to H minus F divided by 2. But all of the variables are the same. So the only difference is it's going to be half of what the tolerance would be on a floating fastener application. Okay. So this is still the tolerance. This is still the MMC of the hole. And this is still the MMC of the fastener. So this is the fixed fastener application. Okay. So now what we need to do is we need to go to our drawings and find the MMC size of the hole and the MMC size of the fastener. Okay. So go ahead. If you have to and you haven't done the drawings yet, pull up the drawing guides, okay? And I want you to find the MMC size of the hole and the MMC size of the fastener. Requires you to remember what the MMC size of a hole, which is an internal feature, is, right? So does anybody know what the MMC size of my hole is? So my H is going to go here. What's the number I'm going to put in for H? And H is going to refer to the clearance hole. What is the number I'm going to put into that spot of my equation? If you're virtual and you know the answer to this, what's the MMC size of that hole? Nope. No, that's the nominal size. And if we want to find the MMC size of the hole, it's what? The largest or the smallest size? This is an internal feature. It's the smallest hole size, right? Smallest hole size. So I'm glad you said 266 because we're not going to take the nominal size because on this dimension, there is a tolerance that's applied, right? Okay. So if the tolerance is not on the actual dimension itself, it defaults to the title block. What are the limits of this hole? What's the largest hole size and what's the smallest hole size?
Smallest hole size will be 0.2555. The largest 0.2665.
Plus or minus 5 thousandths. So if I subtract 5 thousandths.
Oh, I meant 0.2655.
In a calculator, I don't want anybody doing it in their head. In a calculator, do 0.266 minus 0.005. What do we get? 0.261. We want to subtract off just 5 thousandths. That's going to be the smallest size. What is the largest size here? 0.271. Make sure you can get those two numbers. This is plus or minus 5 thousandths, okay? Plus or minus 5 thousandths. This is also a case for, I'm going to tell you, when you have critical parts, and this was at a company that I worked for actually really early on. They didn't want us to leave dimensions like this, especially if it's a critical part. We had to put the limits of size because now you take out of the equation somebody adding or subtracting wrong in their head, right? Because we all think, oh, it's just 5 thousandths off, but you got to have the right decimal place. So be careful with that and check it with your calculator. So when we look at the MMC size of this internal feature, we said it's the smallest size, right? So 0.261 is the number for H in this equation. So this is going to be 0.261. I'm just going to kind of list them here, okay? And then we'll put them into the equation. Be writing this down because you're going to be handing this in. I'll tell you now, I was going to wait till the end and then you would have had to do it all over again. Because some people just sit back and they let everybody else do the work. And then they're just going to put the final number in. And then you won't be able to do it again. So you will be handing this in. I'll add that to our thing. So 0.261 is going to be our H. Our F, the MMC size of the fastener. Okay. See if we can get a clue here. Okay. So the fastener that's going through here is going to thread into a 1/4-20 UNC thread. But that's not what it's asking for. It's not asking for the MMC of the thread. It's asking for the MMC of the fastener that goes through there. Do you guys remember the MMC size of fasteners? It is the nominal size. Yes. So since we have a 1/4-20, right, because it's going to match the thread that goes in there, that's how we know that's the size of the fastener. We are going to have 0.25 is going to be the MMC size. This is an external feature. That means it's the largest size. That's as big as a fastener can get. It's only going to get smaller. Okay. Now we can put these two numbers up here to calculate our tolerance. So T is going to be equal to 0.261 minus 0.250. And we're going to divide that by 2. What is my tolerance? Everybody should be doing it. So you have 0.0055. Anybody else get that same number? Yep. Okay. Yep. Michael did online. Okay. Excellent. Okay. Now, this is what we calculated, right? So this is the tolerance value that we're going to be putting into the feature control frame here. And we're going to be adding a feature control frame here. Okay, now before we do, I'm going to show you a couple things. We calculated our number to be to 4 decimal places, right? But you're going to notice that the tolerance of the size of that hole is to 3 decimal places. Are we going to put a 4 decimal places in a feature control frame for a 3 decimal place part? Go like this. Nope. Nope, we're not. Jesse's might, but he might get points off. No, he was just kind of joking. I think you were joking, right? Saying yes. All right. So what we want to do is we need to make a 3-place decimal here. Now, this is going to be your call. This is 0.0055. Okay. So that means that we could round this up to either 0.006 or keep it at 5 thousandths. This would be the discretion of the designer, depending on how accurate they want it to be. Okay. I personally, to me, this is not super accurate. These are clearance holes. I would go to a diameter of 0.006. Okay. But the number of decimals that you use in your feature control frame have to coincide with the number of decimals on the feature. Got it? Okay. That's really important. Okay. Now, the next thing that you're going to notice is we have an MMC modifier. If you remember back, MMC modifier is used for clearance hole situations. So we're going to keep that MMC modifier there. But then we have datums A, B, and C. Okay, A, B, and C. So we want to find where those datums are on here. I already identified them for you. The primary datum A, not because it's the first letter in the alphabet, because it's the first from reading from left to right. The primary is going to be the main mating surface. So this faceplate is going to mate on this back surface right here. Okay, that's the surface that is actually going to contact the surface right here on the front of our frame. Okay, so that's going to be our datum A. All right, then you're going to notice datum B is in line with the dimension for the height of our part. That means something different than if this was slid over. Is this a feature of size application of the datum where it would control the center plane? Or is this a surface where the bottom surface here is the datum?
Feature of size.
How do you know? It is a feature of size because it's in line with the dimension. So we are actually saying that the middle of this part is the datum. Okay. Now, the reason we're doing that is because these parts are symmetrical vertically and horizontally. How far they are from any edge does not matter to us. It just matters that these 4 holes are going to be spaced appropriately in order to line up with the holes that we want them to. So we're going to say, okay, whatever the size of this is, the center plane is going to be created there. And now we're going to evenly distribute the location of those holes on either side. And the dimension for the vertical application of the dimension is right here, right? This is the 2 inches between. Notice we do not have anything coming from an edge to get down to that 2-inch dimension because we have a datum that is about a center plane. We want to evenly distribute it. So when this is 2.5, I'm going to measure. It's a 2-place decimal. It's going to have plus or minus 20 thousandths. Wherever it is in that tolerance, what that final number is, I'm going to evenly space my 2 inches off the center of that part. Does that make sense to everybody? Okay. Now, the 2 inches, that's a location dimension. You need to put a basic dimension around that number. Why do we do that? Exactly, Greg. I do not want to apply my title block tolerance to my 2 inches. What am I going to apply? It has to have a tolerance, right? Every dimension on a drawing has a tolerance. But in this case, I'm not going to the title block. Where am I going for my 2 inches?
GD&T.
Did you say the feature control frame?
Yeah.
Yes, that's exactly it. Yes. So this is where our tolerance comes from for that. So it's not saying that there's not a tolerance. It's like you're just not looking to the title block. You're looking to the GD&T associated with the feature that we're finding the location for. Okay. So that's vertically. The next datum we have is datum C. Datum C is in line with the width dimension. Is that a surface or a feature of size? Same thing as B was, right? That was a feature of size. So since this is in line, this is a horizontal dimension, I have a center plane going right down the middle here. And now the horizontal dimension for these two holes is going to be evenly spaced about that center plane. Notice there are no dimensions going to the side of the part. Okay. Because of this location, this also has to be a basic dimension. Okay. All right. Since most of you had SolidWorks with me, you remember how to put a basic dimension on? I had to look around because I was like, oh my goodness, it's been a little while. Let me open up this faceplate dimension or face. This is 40. This is the drawing. So if I open up, this might take a little bit. Hope it does. Seems like it's working. I just want to show you where it's at because it's not super obvious. Well, I'm locked up. If you need help with that, let me know. I think it's I don't remember. Yeah, I thought it might have. Yeah, I'm locked up. So unfortunately, I'm going to go back. I'm going to go back underneath here. We'll go back to SolidWorks in a little bit, but make sure that you make those two dimensions that are associated with the position of that feature to be basic. Okay. Now, another thing you're going to notice is that we have on datum A, we have a flatness tolerance. Why do we have that there? Do you guys remember what that's called? It starts with a Q. We qualify that surface. Okay, we qualify that surface. We qualify that surface by making it nice and flat, and now everything else can be dimensioned off of it. That's why it's first of all, it's the main mating surface, so it's going to contact the surface really nicely. But also notice that we are now putting the position of those holes, orientating them perpendicular to that nice surface. Okay, if we don't do that, depending on if it's a critical part or not, but it's mostly if you machine parts, it's going to be something that machinists usually do. They find where the first datum is, they make that nice and flat, they do a machine finish cut on there, and then they go, everything else comes from that. So notice that I have a value for you to put in there. You need to add a value here. Okay. This is a surface callout. Notice that it's not in line with the dimension. It's a surface callout. So on that surface, we need to refine upon the amount of flatness that you would get from the dimension you see here. Okay. So on this dimension, on the width, this is a 3-place decimal. Your tolerance comes from down here. What's my total tolerance or my total flatness on that surface without putting flatness on? How much is it? Nope, not 5. It's plus or minus 5. So it's 10 thousandths deviation, right? So on this surface, we can go up and down 10 thousandths. I'm saying that's not enough. So you need to make this a number less than 10 thousandths. Okay, it can't be 10 because I'm already getting 10 with this number. We only add GD&T on a surface when we want it to be a refinement on what the dimension already allows. Okay, so something less than 10. That's what you need for there. The other one that we have down here, we are going to position these two features of size. The two features of size are the threaded holes. These threaded holes are only here to hold that ram kind of in place or to keep it kind of up against, so it doesn't rattle around in there a lot. And so there's going to be 2 screws that we're going to be putting in place. So you'll notice that they don't line up with another threaded feature on the head here. Okay. So all we need to do is we just need to position them so that they're, they have a cylindrical tolerance zone. So if you had 6 thousandths up here, you may or may not know, that's not a big tolerance, okay? I would probably reuse the 6,000s right down here as well, because those were lining up with something. These don't need to. So using 6,000s is appropriate, okay? You could use 10,000s here and you still would be okay, all right? But I think it makes sense to use 6. The other thing, it was called to my attention that this should say 2 by instead of 4 by. So I'll update that on the guide, but there's only 2 holes, not 4. Okay. Now, because we're using position here, notice that they're using the same datum scheme, A, B, and C. As we look at A, it needs to be perpendicular to A, which we know. B, you're going to notice that that sets up that vertical distance, okay? So on the center plane, then the vertical dimension, 1 inch, needs to be basic as well, right? Because we don't want it to go to the title block. And then when we look datum C, we want that to be centered on datum C, but it is on center already. So that just means it's going to share the same center. There is no horizontal dimension here to make basic. Okay, it's going to share the center plane of datum C, which is the width of our faceplate. Okay, so same datums that you see there. Okay, so what you've done here is if we look at our list for the GD&T application, oh, I gotta do one more thing before I go. I'm sorry. Then what you're gonna do on the front plate of our frame, our feature control frame for position of these 4 holes is gonna have the same diameter of 6,000s and maximum material condition. And then you're gonna identify 3 datums that mimic what we just did on our last part. I'm gonna let you guys finish that up. So mimic the same datums that we did here, okay? So main mating surface for the primary, and then locating on the center planes like we did here for the 2 orientations or the 2 directions of the holes. You have stuff here. So I just want you to reapply that. I'm gonna let you finish that part up, okay? Make sense? All right. So that's the first 2 on our GD&T application. So number 1, the 2 places for position. You also applied 1 flatness on that part as well. Okay, so you got that one taken care of. You got to find 2 more places to use flatness. All right, 3 places to use perpendicularity and 3 to use parallelism. All right, and again, you're going to just create me a document giving me a review of where they're at, like on what parts you did it. You don't have to go into great detail. It's just so that I don't have to search and try to tally them all. This way I can focus when I look at your assembly and I can, or on your detailed drawings, and I can then just know exactly where they're at for you. Does that make sense to everybody? Okay. So this will be handed in probably at about the same time when you do your details. Okay. Because you're going to incorporate this stuff into your details as well. All right. So that's the GD&T part. Are there any questions to kind of finish this up? Okay. Make sure that you add the calculations that we just did as well. I want to be sure that we have that. Okay.
As a PDF.
Yes. Yeah. You can scan it like a picture. So if you're on your phone, I think you can, it's easier to update just or load like a JPEG, right? That would be a picture from your phone. So you can do a JPEG as well for that. Okay, so that's the GD&T application. Then I'm going to stop the recording here if there are no questions.